Hello, everybody. My name is Camilo Vasquez. I work at the Pattern Recognition Lab at the Frederick Alexander University in Erlangen, Germany, and in the University of Antioquia in Colombia. In this video for ICASSP, I will talk about my paper, Comparison of User Models Based on GMM-UBM and I-Vectors for Speech, Handwriting, and Gait Assessment of Parkinson's Disease Patients. So Parkinson's disease is a neurological disorder characterized by the progressive loss of dopaminergic neurons in the midbrain. It is the second most prevalent neurological disorder in the world. In addition, the disease produces several motor and non-motor impairments and affects all of the subsystems involved in motor activities like speech production, walking, or handwriting. The main motor symptoms exhibited by patients include bradykinesia, rigidity, resting tremor, dysarthria, among others. In addition, the severity of the motor symptoms is evaluated by neurologist experts with the third section of the MDS-UPDRS scale. In general, the evaluation of the motor symptoms is crucial for clinicians so they can make decisions about the medication or therapy for the patients. The analysis of signals such as gait, handwriting, and speech helps to assess the motor symptoms of the patient, providing to clinicians with information to make timely decisions about the treatment or the therapy of the patients. According to the literature, most of the related studies consider only one modality, and multimodal analysis, like those ones considering information from different sensors like speech, handwriting, gait, or electromyography, among others, have not been extensively studied. The main reason for that is the lack of available multimodal data for the assessment of the patients. Previous studies, we also showed that the combination of different modalities is helpful to improve the accuracy of the prediction of the neurological state of the patients. So we propose here is the use of speech, handwriting, and gait features to evaluate the neurological state of the patients. The prediction is performed with user models based on Gaussian mixture models, universal background models, or GMM-UBM, and I-Vectors. So this is one of the few studies for multimodal analysis of Parkinson's patients, and to the best of our knowledge, the first one that considers multimodal user models to evaluate the neurological state of the patients. The method proposed here is summarized in the figure. Different features can be obtained from speech, handwriting, or gait signals. Then, data from healthy control subjects are used to train user models based on GMM and I-Vector systems. For the case of the GMM-UBM, data from patients were used to adapt the UBM into GMMs, creating a specific GMM for each patient. On the other hand, for the I-Vectors, we create reference I-Vectors with data from healthy controls. Thus, I-Vector extracted from the patients can be compared with those references. Finally, distance measures are computed between the reference models and those extracted from the patients. And finally, the distance are correlated with the neurological state of the patient based on the clinical score administered by clinicians. So the first part of our method is the feature extraction process. Regarding speech signals, we define 4 different feature sets. The first one is phonation. In this case, the features are designed to model abnormal patterns in the vocal fold vibration of the patient and include jitter, shimmer, amplitude perturbation quotient, pitch perturbation quotient, and the first and second derivatives of the fundamental frequency. The second speech feature corresponds to articulation. In this case, we aim to model the difficulties of the patient to start or to stop the movement of the vocal folds. The features are based on the energy content in the transition between voice and unvoiced segments, or onset. We consider the energy in 22 critical bands according to the Bark scale and 12 male frequency cepstral coefficients with their respective first and second derivatives. The third speech feature set is prosody. Is designed to model monotonicity and monoloudness aspects from the patients. For this case, the logarithmic of the fundamental frequency and energy contours of voice segments are approximated using a 5-degree polynomial. to model factors like the slope, the curvature, the inflection points, among others. These coefficients of the polynomials are then used for the feature set. Finally, our fourth speech-based feature corresponds to phonological posteriors. These phonological features are represented by a vector with an interpretable information about the placement and manner of articulation, and corresponds to the posterior probability of a speech frame to belong to one or more phonological classes, like stop, nasal, or vocalic, among others. We consider a total of 18 different phonological classes, estimated with a parallel bank of recurrent neural networks with bidirectional gait recurrent units, as we show in previous studies. Regarding our second modality, online handwriting, the features are based on the trajectory of the strokes in vertical, horizontal, radial, and angular position. We compute the velocity and acceleration of the strokes in different axes, in addition to the pressure of the pen, the azimuth angle, the altitude angle, and their derivatives. We consider as well features from the inert movement before the patients put the pen on the tablet surface. Now, regarding gait analysis, we compute two different feature sets. The first one corresponds to spectral features designed to model the spectral well and the harmonic structure of the gait signals obtained from inertial sensors. First, we compute the continuous wavelet transform from the acceleration signals. Then, our feature set is formed with the energy content in 8 frequency bands from the scalogram, 3 spectral centroids, the energy in the first, second, and third quartiles of the spectrum, the energy content in the locomotor band, in the freeze band, and the freeze index, which is the ratio between the energy in the locomotor and freeze band, and it's related to the presence of freezing of gait episodes in Parkinson's disease. Finally, our second feature set comprises a nonlinear dynamics analysis. So, gait is a complex and nonlinear activity that can be modeled with nonlinear dynamics features based on the attractor reconstruction according to the Takens theorem. The figure here shows the reconstructed attractor for gait signals from the healthy subjects in the left and a patient in the right. Note especially the chaotic behavior observed for the case of the patient, while for the healthy subject, the trajectories are well defined. Different features can be extracted to assess the complexity and stability of the walking process, including the correlation dimension, the largest Lyapunov exponent, among others. The first user model considered here corresponds to GMM-UBM systems. The main hypothesis is that speech, handwriting, or gait impairments of Parkinson's patients can be modeled by comparing a GMM adapted for a patient with a reference model created with recording from healthy subjects. The model for each patient is adapted from the UBM following a maximum a posterior adaptation process. Then, the neurological state of patients is estimated by comparing the adapted model with the UBM using a distance measure. We use the Pataharria distance, which considers differences in the mean vectors and the covariance matrices between the UBM and the user model. Our second user model is based on I vectors, which are used to transform the original feature space into a low-dimensional representation called total variability space. For this study, we aim to capture changes in the speech, handwriting, and gait due to the presence of the disease. Similar to the GMM-UBM, in this case, we train the I vector extractor with data from healthy subjects and compute reference I vectors to represent healthy speech, handwriting, or gait. Then, we extract I vectors from the patient and compute the cosine distance between those patient I vectors and the reference I vectors created from the healthy subjects. So, regarding the data for this study contains signals collected from 106 patients and 87 healthy subjects. All of them have similar age and gender. All of the subjects are Colombian Spanish native speakers, and the patients were labeled according to the MDS-UPDRS-3 scale, and most of them are in initial or in intermediate stage of the disease. Speech signals were recorded with a sampling frequency of 16 kilohertz. The participants were requested to perform different diadochokinetic exercises like the rapid repetition of pataka, reading isolated sentences, reading text or monologues. Online handwriting data were collected with a specialized tablet with a sampling frequency of 180 Hz. And the tablet allows to collect 6 different signals, including the X and Y positions, inner movements, azimuth and altitude angles, and the pressure of the pen. The subjects perform different tasks, like writing different stuff and drawing different geometric shapes, like the Archimedean spiral to observe the figure for a healthy control and a patient. Finally, regarding gait data, we collect signals with three-dimensional accelerometers and gyroscopes attached to the lateral heel of the shoes. In both feet, as it is observed in the figure in the bottom right part of the slide, the gait signals have a sampling frequency of 100 Hz, and the subject also performed different exercises like 20 meters walking with pauses every 10 meters or heel-toe tapping, among others. To summarize a little bit, data from healthy subjects is used to train the UBMs and the eye vector extractor. For the GMM-UBM system, data from patients were used to adapt the UBMs into specific GMMs. Then, the Bata-Harria distance is used to compute the GMM and the UBM. For the eye vectors, a reference was created by averaging the eye vectors from the healthy subjects that have same gender and similar age of the patients. Then, eye vectors from patients can be compared to reference eye vectors using the cosine distance. Finally, the distance are correlated as well with the MDS-UPDRS-3 score of the patient. So the Spearman correlations between the neurological state of the patient and the user models based on GMM and eye vectors is shown in the table for speech, handwriting, and gait features. A strong correlation is obtained with the spectral features regarding gait analysis. The model with the model based on the GMM-UBM. This is expected because most of the items used by the neurologists in the clinical evaluation are based on the movement of the lower limbs. For the handwriting features, we observe weak correlations, especially with the eye vector systems. Finally, the correlations obtained with speech features are not robust enough to model the general neurological state of the patient. This result is explained because the MDS-UPDRS is a complete neurological scale that considers speech impairments in only one of the 33 items. However, all features can be complementary to improve the results. The user models extract from all feature sets using the GMM-UBM systems were combined by concatenating the distance between the user models and the UBM for each feature set. A linear regression was trained with the metrics of distances to predict the MDS-UPDRS-3 scale. The model was trained following a leave one out, subject out cross-validation. We observed that the Spearman correlation increases by 2.4% absolute with respect to the one obtained only with the gait features. So the figure here shows the error in the prediction of the clinical score of the patient. Most of the patients are in initial or in intermediate stage of the disease, and they were predicted with the same distribution. The outlier in the top of the figure corresponds to the eldest patient in the corpus. Now this figure shows the contribution of each feature to the multimodal user model. Each bar indicates the coefficient of the linear regression associated to each feature set. Spectral features were the most important, followed by prosody and articulation features. For the case of handwriting, they were less important than expected. However, it could be because the extracted features are based on a standard kinematic analysis that might not completely related to the symptoms associated with the disease. Now, to conclude, the present study compared user models based on GMM-UBM and eye vectors to evaluate the neurological state of the patients using information from speech, handwriting, and gait. Different features were extracted from each biosignal, and gait features showed to be the most accurate to model the general neurological state of the patient. However, the combination of the different biosignals improved the correlation of the proposed method. Regarding future experiments, we believe that better results could be obtained if more training data from healthy subjects is available, so we can create better reference models, especially from handwriting and gait. Further studies will consider as well additional features to model other aspects of Parkinson's symptoms, especially from handwriting. At the same time, additional fusion methods can be considered to evaluate the neurological state of the patient. So this is everything from my side. Thank you very much. I'm open to any question, comment, or possible collaboration from the person in the audience.